Assalamualaikum and hi everyone. We are from group RAS 256 4A and today we will presenting about our RAS mini project for MRS600 MARINECULTUre. So, recirculating aquaculture system or RAS are modern aquaculture system that continuously filter, treat and reuse water in a closed loop environment. Unlike traditional fish farming, RAS recycles up to 90 to 99% of the water through mechanical and biological filtration. Mechanical filter remove solid waste, while biofilter use beneficial bacteria to convert toxic ammonia from fish waste into nitrate. This process maintain good water quality and reduce water consumption and environmental pollution. The main advantages of RAS include efficient water use, improved biosecurity, stable water quality, and year-round production. This control condition help improve fish growth, reduce disease outbreaks, and make aquaculture more sustainable. For your information, Nile tilapia or Oreochromis niloticus was selected because it is one of the most widely farmed freshwater fish in the world. It grows quickly, has a high survival rate, and can tolerate relatively high stocking densities, making it ideal for RAS. Tilapia grows best at temperature between 26 to 30 degrees Celsius with a pH of 6.5 to 8.5 and dissolved oxygen above 5 mgl. This condition can be easily maintained in a RAS. Since tilapia produce ammonia as waste, the biofilter plays an important role in converting ammonia into nitrate, ensuring a safe and healthy environment for the fish. Then, for plant, golden photos or Epipremnum aureum was chosen because it is a fast-growing plant with excellent nutrient uptake. Its roots efficiently absorb nitrates and other nutrients produced from fish waste, helping to improve water quality before the water is returned to the fish tank. Golden photos is also hardy, easy to maintain, and adapts well to hydroponic conditions, making it suitable for integration with RAS. Nile tilapia and golden photos complement each other in a closed-loop system. Fish waste provide nutrients for the plants, while the plants remove excess nutrients and help purify the water. The clean water is then recirculated back to the fish tank. These natural nutrient cycles reduce water usage, minimizes waste discharge, improve fish health, and support sustainable aquaculture. Therefore, the combination of Nile tilapia and golden photos is an effective and environmentally friendly choice for a recirculating aquaculture system. Then, for objective for this mini project are to optimize design, creating functional layouts that maximize space and resource efficiency. And second, environment control, precise management of water quality, temperature and metabolic waste. And the last one, scalability, designing system that can grow from small pilot projects to industrial scale operation.
Next, I will talk about the experimental design and setup. We use two fish tanks for the recirculating aquaculture system, also known as RAS. Both tanks has the same size, which is 91.5 cm long, 46.5 cm wide, and 45.5 cm width. When these tanks placed together with a small gap between them, the two tanks can take up to a total length of 193 cm. Next, we have a filter tank. It's 125.5 cm long, 45 cm depth, and split into 4 sections. The sections measure 40 cm, 27.5 cm, 33 cm, and 25 cm. Each section holds a different filter material. The filter tank width is 45.6 cm, close to the fish tanks. Now, Let's look at how the water flow through the RAS. First, water leaves the fish tank through the outlet pipe that show in orange color and flow down into the filter tank. Inside the filter tank, the water passes through the section in the order of coral, charcoal, biobos and filter wool, then lastly spun with the water pump. After filtering, the water pump push the water back up through the inlet pipe that show in red and return it to the fish tank. Above the coral section, there is also a small plant bed, so the system works like a simple aquaponic setup. For the pipes, the inlet pipe is 108.4 cm long, and the outlet pipe is longer at 172 cm since it needs to reach across both fish tanks. From the image below, you can see the actual setup. The two fish tanks sit on top and the filter tank with a 4 section sits below, all connected by the same pipes.
So next, I will explain about the filtration system in RAS. The function of filtration system is for maintaining the efficiency for overall productivity of RAS. Next is to provide for most water quality for the tank and environment for the fish to grow while maintaining the sustainability of the system to the environment. Filtration system also can prevent the accumulation of toxic substance and excessive fish waste in the tank. There are three types of filter. The first one is mechanical filter. Mechanical filter is to remove solid waste material from the water, such as fish waste, uneaten fish food, and suspended particles. Mechanical filter also can maintain the water clarity, preventing clogging, and ensure the efficiency for overall RAS operation. The example for mechanical filter is filter wool and filter sponge. Next is biological filter. Biological filter can provide a surface for colonization for nitrobacter to grow. The nitrification process will undergo, which involve nitrosomonas bacteria to converting toxic ammonia into nitrate. This nitrobacter can convert nitrate into less harmful nitrate. This less harmful nitrate is very useful and important for the plant to grow. Biological filter also can create a healthy water environment for cultured fish. The example for biological filter is biobulbs and corals. Next is chemical filter. The function of chemical filter is to remove the soft organic material and odors while absorbing harmful chemical and toxin contained in water. The example of chemical filter is activated carbon or charcoals. Here, as you guys can see, the water will come out from the output pipe and the plant will receive first the unfiltered water in order to receive a nutrient and nitrate to growth. And then the water will pass through all the stages of filtration to filter all the toxic material and suspended particles. And the water will pump back from the pump to the water tank. Here, as you guys can see, the water will come out from the output pipe and
next, in this section, I will explain about our work schedule and student involvement for managing the RAS system. This table shows the weekly duty schedule for all team members. Each day is divided into a morning shift and an evening shift. Every member is assigned to a specific shift to ensure that the RAS system is monitored every day without any interruption. During each shift, the assigned member is responsible for feeding the fish, checking the water flow, monitoring the water quality, inspecting the fish for any sign or illness or mortality, and making sure that there are no blocked pipes or equipment issues. Next is the task rotation mechanism. We use a weekly rotation system so that every team member has the opportunity to perform different tasks. This creates a fair schedule give everyone a hands-on experience in operating the RAS system, and prevent the same person from being overloaded with the same responsibilities. For best practices, every member follows the same standard operating procedure during their shift. We carry out routine inspection, record our observation, and report any issue immediately. This helps us to detect any problem early and maintain a healthy environment for the fish. Finally, teamwork and consistency are very important for the success of this project. Good communication between team members ensure that important information is shared during the shift change. Every member is expected to complete their duties on time, stay committed to their responsibilities, and support one another whenever any problem occurs. By working together consistently, we can ensure that the RAS system operates efficiently and the fish remain healthy throughout the project.
Next, I will explain the water quality monitoring conducted throughout the study. Water samples were collected from the culture tank and monitored once a week for a total of 10 weeks. And the purpose of monitoring this parameter was to evaluate the water quality and the effectiveness of the biological filtration system in maintaining a healthy environment for both fish and plants. Several parameters including temperature, pH, dissolved oxygen, ammonia, nitrate, and phosphate were monitored using the appropriate measuring tools as shown in the table. Each parameter plays an important role in this system. Temperature, pH, salinity, and dissolved oxygen directly influence the fish metabolism, growth, respiration, and the activity of beneficial bacteria. Thus, maintaining this parameter within the optimal range helps ensure a good fish health and efficient biological filtration. Sudden changes in this parameter can stress the fish, reduce biological filtration efficiency, and negatively affect the overall performance of the system. Another important aspect of water quality is the nitrogen cycle. Ammonia is produced from fish excretion, uneaten feeds, and the decomposition of organic matter. Since ammonia is highly toxic to fish, beneficial bacteria convert it into nitrate and finally into nitrate, which serve as an essential nutrient for plant growth. Similarly, phosphate, which mainly originates from fish feeds and fish waste, is absorbed by plants, helping to improve water quality while supporting the plant growth within the system.
Next, I will discuss the water quality parameters based on the results obtained over the 10-week culture period. Let's start with the physical parameters. The water temperature ranged from 24 Celsius to 32.3 Celsius. Although there were some fluctuations, the values remained within the tolerant range for Nile tilapia, which is approximately 20 Celsius to 35 Celsius. However, the higher temperature recorded in week 5 could have increased the fish metabolic rate and oxygen demand. Salinity remained constant at 0 ppt throughout the experiment, confirming that the RAS maintained a stable freshwater environment suitable for tilapia culture. Finally, the pH remained stable between 7.35 and 7.82, which falls within the optimum range for tilapia. This stable pH also supports the activity of nitrifying bacteria that are responsible for converting toxic ammonia into less harmful compounds. Moving on to the chemical parameters, the dissolved oxygen or DO ranged from 1 to 6 milligrams per liter. The lowest DO level was recorded during weeks 4 and 5, which is below the recommended level for optimum tilapia growth. Low dissolved oxygen can reduce feeding activity, slow fish growth, and also affect the efficiency of the biofilter. However, the DO level gradually improved in the later weeks, indicating that the aeration or water circulation becomes more effective. The most significant finding was the ammonia concentration. It increased from 0.25 milligrams per liter in week 1 to 8 milligrams per liter from week 2 onwards and remained high throughout the experiment. This suggests that the biological filtration system was unable to remove ammonia efficiently. Since ammonia mainly comes from fish waste and uneaten feed, the consistently high concentration may indicate that waste production exceeded the capacity of the biofilter. Finally, nitrate remained low for most of the experiment except for a temporary increase in week 9. Nitrate remained between 5 and 10 milligrams per liter, indicating that nitrification was taking place. Phosphate was highest during the early weeks before gradually decreasing, suggesting that waste management and filtration become more effective as the experiment progressed.
Assalamualaikum. Next, I will tell about fish growth measurement. To evaluate fish growth within our recirculation aquaculture system (RAS), we track 4 key physical dimensions weighed in grams: cranial profile, body depth, and skeletal length, to ensure our fish are developing a healthy, balanced mass. In an RAS environment, this tracking acts as a vital diagnosis tool to confirm that our water quality monitored to distinct size cohort. Tank 1 started with smaller fingerling at an average of 7.4 grams, while Tank 2 hosts a larger cohort averaging 28.7 grams. By the end of the monitoring period, Tank 1 nearly tripled its mass to reach a final average of 21.8 grams, and Tank 2 scaled up to a robust 44.3 grams, giving us clear confirmation that the overall biomass in our system is steadily expanding. Next, when we break this weight gain down into specific morphometric measurements, we see excellent anatomical symmetry and structural uniformity across both groups. In Tank 1, the younger fish experience rapid skeletal expansion, with the average total length surging from 2 cm to 10.68 cm, alongside a healthy increase in body depth from 2.5 to 3.24 cm. Meanwhile, the older cohort in Tank 2 demonstrate a more consolidated growth curve typical of maturing fish, filling out their muscular thickness to a 4.23 cm average body depth and reaching an impressive final total length of 13.84 cm. Ultimately, this proportionate advancement in both skeletal structure and muscle mass prove that our RAS parameters, stocking densities, and nutritional strategies are working exactly as intended for high yield development.
Next, I will present the plant growth measurement in our aquaponic system. The plant used in this experiment was pothos, also known as devil's ivy with the scientific name Epipremnum aureum. Pothos is a fast-growing evergreen vine with heart-shaped leaves. It grows well in water, absorbs nutrients efficiently, and is commonly used in aquaponic system because it helps improve water quality by removing excess nutrients. There are a total of 10 pothos plants that we used in this experiment. This table shows the initial and final measurement of the 10 pothos plants. The 3 growth parameters that were measured are petiole length, leaf width, and leaf length. Based on the average values, the petiole length increased from 6.1 centimeters to 6.6 centimeters, while the leaf length increased from 5.4 centimeters to 5.9 centimeters. However, the average leaf width remained unchanged at 4.0 centimeters. So overall, these results indicate that the pothos plants show a positive growth during the experiment. The increase in petiole length and leaf length indicates that the photos plants experience a healthy vegetative growth. A longer petiole help position the leaves to receive more sunlight, while longer leaves increase the surface area for photosynthesis. This allows the plant to produce more energy for growth. Although the leaf width did not change, this does not necessarily indicate poor growth. Since the experiment was conducted over a relatively short period, and the plants may have focused on leaf elongation rather than increasing their leaf width. So the aquaponic system provided suitable conditions for this plant growth. The fish waste was converted by beneficial nitrifying bacteria into nitrate, which served as a natural fertilizer for the plants. Throughout the experiment, nitrate concentration ranged from 5 to 10 milligrams per liter, while the pH remained stable between 7.3 to 7.8. So this condition supported nutrient uptake and a healthy root development. Therefore, we can conclude that the aquaponic system successfully supported the growth of these pothos plants, it demonstrating its suitability as a plant species for aquaponics.
Next, I will present the fish mortality record throughout the 10-week culture period. Fish mortality was monitored weekly in both Tank 1 and Tank 2. At the beginning of the mini project, Tank 1 contained 1 egg for tilapia, while Tank 2 contained 1 for 3 tilapia. During the 10 weeks, the number of fish that varied from week to week. There are several possible reasons for the fish mortality. The first reason is water quality fluctuations. Changes in dissolved oxygen, ammonia concentration, pH, or temperature can stress the fish. In a recirculating aquaculture system, fish waste and uneaten feed produce ammonia. If the biological filter cannot remove ammonia efficiently, it accumulates in the water and becomes toxic to the fish. Low dissolved oxygen levels can also reduce fish respiration and increase mortality. Another possible cause is aggressive behavior or cannibalism among the tilapia. Although tilapia are generally considered less aggressive than some other species, they may attack smaller or weaker fish when there is competition for food, limited space, or differences in fish size. Injured fish become stressed and are more likely to die or develop infections. In addition, handling stress during fish sampling, weight measurement, or routine maintenance may have contributed to fish death. This frequent handling can weaken the fish and reduce their resistance to environmental stress. Overall, the mortality patterns show that maintaining good water quality, ensuring efficient mechanical and biological filtration, providing sufficient aeration, avoiding overfeeding, and reducing fish aggression through proper stocking density and regular size grading are important to improve fish survival in a recirculating aquaculture system. In conclusion, this mini project successfully supported the culture of tilapia by providing a controlled environment with efficient water filtration and reuse. Throughout the project, regular monitoring of water quality parameters, fish growth, plant growth, and fish mortality demonstrate the importance of maintaining stable water conditions for healthy fish production. Overall, this project achieved its objective by demonstrating the effectiveness of RAS in supporting sustainable aquaculture while providing valuable practical experience in system operation, water quality management, and fish health monitoring.
Based on this mini project, there are several recommendations that can be made for the future. First, automatic water quality sensor that can be installed to continuously monitor important parameters such as pH, temperature, dissolved oxygen, and ammonia. For the second, The renewable energy sources like solar panels that can be used to reduce electricity consumption and improve sustainability. In addition, future study can investigate different hydroponic plants to compare their nutrient removal efficiency. Finally, conducting long-term experiment would provide more comprehensive data on fish growth, plant performance, and the overall effectiveness of the recirculating aquaculture system. A few of improvements that can also be made to enhance the current system. The biofilter can be upgraded with more efficient filter media to improve ammonia removal and maintain better water quality. The system can also be integrated with IoT technology for real-time monitoring and automatic control to reduce the need for manual operation. In addition, optimizing water circulation and aeration can provide a healthier environment for both fish and plants, making it more suitable for commercial aquaculture while maintaining its sustainability.